a priori itself, it is clear that there is going to be a global maximum and a global minimum, because the function that I'm maximizing or minimizing is a continuous function, y square minus x square, and I'm restricting it to a compact set. So of course the image is going to be compact and therefore bounded and closed. So it's going to achieve a global maximum and a global minimum. And looking at the level curves, we see that the global maximum value is achieved on the y-axis, namely 1 and -1, and minimum value is -1, which is achieved on the x-axis. Okay, very good. So,
sir, I did not understand like why it is compact, sir.
Yeah, so this set M itself is a compact set, right? It's the circle.
Yes, but in general, if H is continuous, like, should it be compact?
No, that it does not mean that, but in this particular case, M is compact.
Okay, sir.
Right? See, for example, if I took H to be XY or something like that, it's going to really depend on the geometry. It's going to depend on the nature of the solutions. It's only in this particular case that M is compact.
Okay, sir.
If it is not compact, then we have to do some kind of, then we really have to look at how to, then we really have to look, if you want to see whether something is a global maximum or minimum. Whereas in case of a compact set, just like when we were, just like in analysis 1, when you found extrema, or in your 11th and 12th standard, when you found extrema over a closed interval, you did not really have to analyze the derivative at all, right? I mean, further analysis after finding critical points. You just find critical points, you find the endpoints, and you just calculate a value, table of values. Whatever is the largest is the maximum, whatever is smallest is the minimum. Same thing applies over here, assuming that your constraint gives you a compact set. Anyway, but what we want to see is that, so it appears, so here, from the way level sets of the F interact with M, here we see that we have maxima at 0, 1, 0 plus or minus 1, at plus or minus 1, 0. But another thing, sort of the interesting point, is that it also appears that at the extrema, the constraint, the constraint graph, let's say, and the level of objective function F are tangential to each other. So this is an important thing. It also appears that. And Lagrange multipliers are going to formalize this observation and give us a method. So first, what does it mean, right? We have to see what does that mean. So you see, what will be useful over here is to understand the notion of tangent space. Okay, so right now what we're saying is two things being tangential to each other. So, well, what are they? What kinds of things are those? See the constraint graph, that itself is a level curve, right? I have defined the function h, and I'm solving it the green graph, it's really the level curve for the function h at level 1. And the other colors, they are level curves for the function f, the objective function. So instead of saying two level curves being tangential to each other, what we will first carefully define is the notion of what it means to be a tangent. Remember, a tangent is something that should be a line, right? So what it means to have tangents to a level curve, that's something that we will define carefully. All right. So we will define tangent space to level curve at a point not level curve, let's say in more general. In this case, it's a curve to okay, so there is no the to a level set of a C1 function at a point P. Okay. So we will come to this, but before that, what I want to do is I want to I want to get the recipe portion of this out of the way. So we will of the objective function at the extremum or infimum.
So you got cut out in the middle. Can you repeat the last 1 minute of what you said?
Sure. Yeah. So what we will do is, before we actually define tangent spaces carefully, we will just go ahead with this intuitive idea that somehow when I'm trying to maximize or minimize an objective function with respect to a constraint, which is a level set of some other function, what seems to occur is what we saw in this picture. That is that the constraint level set and that at a point of maximum or minimum, the constraint level set and the level set corresponding to the objective function, they seem to be tangential to each other. We will just go with this intuitive idea for now and see some examples, and then later on come to this. So here is the thing. So we'll answer this. We will define this later on. But for now, let me just state it here. So for now, understand the recipe. So terminology, let's get this out of the way. So let us say, let U be open in for so the idea is that here I had two variables, a function of two variables, and I had just one constraint, but I could have a function of many variables. So f could be a function of f, x1, x2 up to xn. And the number of constraints that I could have could also be something large. So let us say I have a function of 100 variables and I put 10 constraints on that. So typically speaking, what would be the dimension of the space over which I would want to I'm trying to optimize? I have a function of 100 variables, but I want to regard it only subject to 10 constraints. Let's say 10 independent constraints. Suppose the constraints were all linear constraints. All right, so this is supposed to be a straightforward question. If I have a function of 100 variables, it's some function. Okay, we don't need to consider the nature of the function, what specific function it is. But I want to optimize this function subject to putting 10 constraints on this. And each one of these 10 constraints is just a linear equation. And there are no linear dependencies among these equations. So my domain is no longer a 100 dimensional space. It will rather be what?
90 dimensions.
A 90 dimensional space, right? Of course, if my constraints are not linear, then it becomes a very interesting situation. What is the nature of this constraint set? That itself comes into the picture. And of course, the geometry of the function f also comes into the picture, right? But for now, what I'm saying is the following, that let us consider the case of only one constraint. In other words, f is a real valued function, but the constraint function is also a real valued function, a single real valued function. And I'm saying that I have set its value at a certain number c, and I'm looking at its level set. Okay. So the terminology is the following. So I have an open set, and now I have two functions. F is a function from u to Rn, which is the objective function. And h is also a function from u to Rn, which is the constraint. I haven't really asserted anything about h, so it has not become a constraint, but so want to find. So in other words, up there f was x square minus y square, or y square minus x square, and h is the function x square plus y square. So let me just finish for a moment, and then we'll come back to the question. We want to find extrema of f restricted to the level set m, which is defined to be x in u, such that h of x is some c, right? So in other words, this is just h inverse of c for some constant c, given constant. Okay, so then what do we say? So in other words, so f restricted to m has a local max, let's say at point P m. What does that mean? So that just means that I can find an open neighborhood in all of Rn, okay? Such that means some open.
Sir, sorry to interrupt, but you've marked H as mapping from U to Rn, but C belonging.
Oh,
to R.
I'm so sorry. I'm sorry. That's nonsensical. Thank you very much. So these are real valued functions. Now I'm trying to maximize or minimize them. So they're real valued functions. The set U is open in R. Thank you for that. Okay, so what was I saying? Yeah, so for some means that for some open W in U, f of p is always greater than or equal to f of x for all x, not in W, but W intersection, and has a respectively local minimum if, here I have respectively, f of p is less than or equal to x. Okay. And of course, a local extremum is either a local maximum or a local minimum. So this is the theorem which I'm going to state now, and let us see. There's going to be something wrong with this. I'm already telling you. Okay, we'll find out what is wrong. In the above situation, suppose f and h are C1 functions. Why do we need them to be C1? We will see in the C1 functions from U in R. And as usual, M is the inverse of C. So here is the statement. If F restricted to M has then there exists a unique scalar lambda, a real number such that so I'm just simply saying that the gradients of both of these functions at this extremum point are proportional to each other, right? Of course, what I can say is that the gradient is something that we have a visual meaning for, right? Somehow the word gradient, we have a visual interpretation as we saw last time. But really the gradient as a vector in Rn, it's just the transpose of the derivative as a map from that point. Right? So this is just the transpose of, so this is f prime of p is equal to lambda times h prime. Since the derivative is somehow associated with tangents, this is not an unreasonable formulation, right? The two things are tangential to each other. That means that the tangent directions match. But the value of the derivative need not match. So they are proportional to each other. So at the level of heuristics, this is okay. All right. So, so is the meaning of this clear? In fact, let's do one thing. Let's take this theorem for granted. Again, remember, as stated, this theorem is not quite correct. But we will see examples.
Excuse me, sir.
Yes.
Here, let M is equal to H inverse C, I guess. You have written F inverse.
I'm sorry. I just seem to be making mistake after mistake today. So F is my objective function and H is the constraint function. So of course the set on which I'm optimizing is not F inverse of C, but it is H inverse of C. Thank you. Examples. So let's do the first example once again and see if this is true. So f of xy is equal to y square minus x square, and h of xy is equal to square plus y square, and c is equal to 1. So to crank out the answer is, once you have the recipe in the theorem, then it is not difficult. So what does the recipe say? Let's follow the recipe. Once again, I am guaranteed that there has to be a maximum and a minimum, because in this case the level set is a so m is equal is a circle. So m is equal to h inverse of 1, which is equal to 7 unit circle. Let's follow the recipe. So let's calculate what is the so suppose p is equal to okay, so now how am I going to write down the points? Let's write them. Okay, so p equal to AP is an because this is a very That's really too bad. A point, P is not an experiment. Suppose there exists, suppose F restricted to M as an extremum at equal to A comma B. Then let's just calculate. What is delta F of P? Come on, let's just do this. Well, this is just straightforward calculation, right?
Minus 2a into b.
Correct. So it's going to be, so we just do minus 2x and 2y, but at A comma B, which is minus, or maybe that's a, okay, fine. I mean, we're okay. I mean, I've calculated the derivative as a function and then evaluating it at the point, but it's more directly minus 2a comma b. Okay. What is the gradient for H? So what does the method tell us? So we want to find, or we have some lambda. We know that there exists unique lambda such that minus 2a to b into a to b. On which side do I have the lambda? Let's look carefully. It's multiplying the constraint part. Right? So that means I have to put lambda. So is this possible now?
No, sir.
It doesn't really seem to be possible. No? So is everything wrong?
Well, sir, if A was 0, for instance,
Yeah, correct.
then lambda
So,
would be 1.
right. So if A is 0, then it is possible that lambda is 1. And on the other hand, if B is 0, then
It would be minus 1.
it would be minus 1. So you see, this is leading. By the way, what if A and B are both 0? Then lambda could be anything. No?
In which case, it's not unique, though, right? So that is
Okay. So you're using the theorem to argue this. But notice that A and B cannot both be 0. Why?
Because P belongs to H inverse.
Yeah, that point P, remember, we are doing the optimization subject to the constraint that the point P be on the circle. So A square plus B square has to be 1. So let me write this over here. So A square plus B square is equal to 1. So what this tells, so not possible. Unless one of is 0. And so we get this A equal to 0. By the way, A is equal to 0. That tells me that B is plus or minus 1. And in that case, lambda has to be equal to 1. Because B is non-zero. B is equal to 0 gives me A is equal to plus or minus 1. And lambda is equal to minus 1. Okay, so this is our procedure. So any questions so far?
Sir, in the theorem that we proposed, I mean, it says that we get a non-zero lambda, right?
Does it?
I mean, it does not say yet. I mean, I was just
It does
asking.
not. No, it does not.
Okay.
And that's a question. Actually, keep see for yourself. Does lambda have to be 0? Keep that question in mind. Okay. But this all seems very nice and simple. let's try to go along and see one sort of simple example. All right. So here is the thing. Now I'm going to say that suppose I have the following situation. U is just R2, and the function that I have is the form. So I want to find the extremum of f of x comma y equals y. All right. Subject to the constraint h of x comma y equals y minus some function g of x is equal to 0. This is a very strange way of saying something very simple. So just take a moment to see what this is saying. Some differentiable function. Let's say C1 function, because I'm talking about C1 function. What is this saying? Oh, so keep saying this in the same thing. What does it mean to maximize or minimize f, this function f, with respect to the given constraint?
I think we're just trying to optimize G, right?
Exactly, right? So this is just a way of saying that what does it mean to say that the constraint is true? That means that y has to equal g of x. In other words, for this function h, I'm drawing the level set corresponding to the value 0 in the xy plane. But that is just the ordinary graph of the function y equal to g of x. And on this function, and on this set, which is the usual graph of the function g of x, I'm simply saying what is the maximum value of y. So this is just a way of to say let's okay, so while I'm writing this simple thing, just apply the recipe and see what you get. This is equivalent to as in school. Okay. So what does the recipe give us? The recipe should give us something, the recipe should give us the familiar condition, right? That if I have a maximum, let's say at a point, so suppose p equal to a comma b is a gives, keep saying is, so what's the condition that I should find? Well, let's take a look.
G dash x equals 0.
G dash is equal to 0, right? I mean, and let's see how this comes about. So, what is the? So I will stop writing. Okay, fine. What is that? Well, we calculate partial with respect to x, partial with respect to y at the point a comma b, and just write them as a column vector, right? Instead of a row matrix as a function. So what is it?
0, 1.
0, 1, exactly. And that is supposed to, so should be lambda times
Minus.
yeah.
Oh.
So let's just write this. So lambda times, correct, exactly. Now tell me.
Minus g prime of x.
Minus g prime of, I will write a.
Oh, sorry. Yeah, evaluating at a and then 1.
And then what do I have on the bottom?
1.
1. So do you see how this is, which is to say 1 equals lambda times 1, which gives me lambda equal to, which gives me lambda equal to 1. lambda equal to 1. And therefore, this gives me that 0 equal to lambda and lambda prime minus lambda prime. Okay. So that gives me that G prime of A is equal to 0. Okay. So of course, any new thing that I say should be consistent with things that we already know, right? So this checks with what we have. Okay, so very good. All right. So let me just say as expected. Now here is the third example. All right. So f of x comma y is x squared.
Sir, what are we actually finding in these examples? I mean, we are setting the
Correct. So I did not really complete this, but notice what I am looking at is, you're absolutely right. Thank you for saying that. So the theorem, okay, so let us see what the theorem says. The theorem says that if I have a local maximum or a minimum, then this condition must be met. This lambda is called the Lagrange multiplier. Okay? Or the Lagrange. It is exactly like the one variable situation. I do not know, I want to find extrema. I do not know where they are. So the finding critical points is a way to cut down this entire space, to cut it down to some manageable list. That's exactly what we are doing. What we are saying is that if at point P you have a local extremum, then this condition must be met, the Lagrange multiplier condition. That condition in turn allows me to find out where the extrema can occur. So you see in the first one, I was able to say that, well, the extrema are precisely at the points plus or minus 1 comma 0 and 0 comma plus or minus 1. And then just by looking at the values, because in this case, the set on which I'm optimizing is a compact set, just by looking at the values, I know that whichever one gives me the largest value of f, that is the maximum, and whichever one is the smallest, that is the minimum. So the simple answer to your question is that what we are getting out of this is the candidates for the points P. Lambda is something that allows us to solve for that.
okay, sir.
Right? So we did find the value of lambda, but really what we wanted to find was that A and where, at what points can these maxima or minima? Again, they are candidates. The way to classify them, some other method has to come into the picture. Okay. Now,
sir, in the very first place, when we are saying that suppose this point has an extremum, so are we assuming that our constraint set is compact?
no, we are not. Because if we do not have a maximum or a minimum, then this would be vacuously true, right?
Oh,
But
okay,
notice,
okay, yes, sir.
but notice, let us suppose I have something, like I don't know, something which is just take a straight line with non-zero slope. Even here it helps me, right? Because if I have a maximum or a minimum, then the derivative over there has to be 0. So if I'm not able to find any such thing, then that means that there is no maximum or a minimum.
Okay, so this calculation would also say that.
Right? But what it will not help you is that if there is a maximum or a minimum, then you will find it. But that does not say that whatever you found is a maximum or a minimum. For that, some other analysis will have to be done. Right?
Yes, sir.
Okay. But the point of this example number 2 was that the necessary condition that we get out of this, it's not so much finding the value of lambda. It is giving me a constraint on the point. Of course, lambda is a variable. So sometimes while doing the algebra, you can try to solve for lambda and use that to get the numbers. Right? We will see examples. Okay. Any other questions? Okay, so now do this. So the function that I want to, my objective function is x squared. And my constraint is subject to Okay, so this may appear kind of dumb, and it is, but I want you to work this out and see what's. So before you jump into the recipe, let us just check sort of do a background check. Just looking at this function, does this have a maximum or a minimum? So this is a function of two variables, x and y, right? I am restricting it to y equal to 0. In other words, the domain has now just become the x-axis, correct? And the function is x squared. Does it have an extremum?
Yes, sir, it has a local.
At
It
0.
has it has a global extremum at x equal to 0, right? This is a very silly example, correct? So let's look at the hypothesis now. The hypothesis say, well, whatever, yada, 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 whatever. These are C1 functions. I mean, the functions are x square and y. You cannot hope for more innocuous functions. So apply the recipe and see what you get. All right, so does it work out? Do I get the origin?
Yes,
Yeah.
sir.
Okay, let's see what happens. Okay, so what is the gradient of f at a comma b? Let's just do this in terms of x and y. So what is this?
2x0.
And what is this?
0, 1.
What's the conclusion?
Lambda has to be 0.
Okay. But okay, I see. So all right. This is equal to, so this is actually, so this is equal to lambda times, which is lambda. Okay, all right. So this, so lambda equal to 0 and x is equal to 0. So this worked out. All right. So I wanted to achieve something over here, which I failed to achieve because I did this example too quickly. You know what? I do need to add something over here, but I failed to show this to you. If some conditions. So and so let me not try to come up with this with an example on the fly, but let's continue. So sorry, that was, I have to just, in case it was not clear, I failed to do something I wanted to. There is an extra condition which I wanted to show that was necessary, but in this example it didn't come up. All right, let's do a couple more. So f of xy equals xy. Subject to, so this is an example straight from square by okay. You look at this example, and I want you to do this as a, just as practice in applying the recipe. But you look at this example, and do you notice one thing? Essentially, this example is no different from example 1. Why?
You can sort of rescale your coordinates to make it a set.
Yeah, so just look at the objective function. It's xy. Over there it was x square minus y square. Well, okay, level curves are hyperbolas in both cases, right? Just rotated. And what is the constraint? Over there the constraint was a circle. In this case, what is the
An ellipse.
constraint?
Ellipse.
It's an ellipse. So you see, geometrically, nothing much has changed. But as practice, you can just do this. So maybe just take a couple of minutes to do this. And then I will give you one more. Find or do something. Okay, I'm really just following Pramad's notes here. So let's say closest from some point. Okay, but maybe so he has a specific example. So let us say ABC. I don't know how easy it is going to be to do in terms of ABC. And maybe I'll also just say 3. Something. Okay, in fact, you know what, let's just so okay, so for number 4, okay, it's going to be a matter of calculation, which we will do quickly. But for number 5, geometrically, do you see what is going to happen? For this arbitrary point,
So the line joining the origin and E comma B comma C will intersect the sphere at 2 points.
correct,
Those
exactly.
will be the 2 points.
Those will give. And of course, there is going to be one case where this is not going to work.
If the point is the origin.
The point itself is the origin. And if the point itself is the origin, what is going to happen? I mean,
So all the points are equally spaced from
right,
E comma
exactly.
B comma C.
And so Lagrange multiplier should actually perhaps tell us this, okay, or fail. But okay, so here is the all right. So let's just do this. So what happens with number 4? We'll follow the exact same recipe, delta F. Well, anyone? Can you just read this out?
Y X.
Lambda times delta H, which is equal to lambda times what? Two x by 9 and
Y by 2.
y by 2, y by 4, so y by 2. Okay, so now what do we do? You see, now algebraically this has become a little more complicated, right? So what this says is that y is equal to lambda times 2x by 9 and x is equal to lambda times y by 2. But also I know that x square by 9 plus y square by 4 is equal to 1. In other words, this is 3 simultaneous, 3 equations in 3 variables. So, so there is a matter of now solving, correct? So what can we do?
Sir, I substituted x is equal to lambda y by 2 into the first equation.
Right.
So I
And
got an equation in terms of y and lambda,
correct.
and I get that either y is 0 or lambda is equal to plus minus 3.
Okay.
Well, what
So
I get
now,
was 0 is into lambda squared by 9 minus 1 is equal to yeah.
correct. Okay. So now, okay. So y is equal to. So I'm just going to say algebra. Lambda equal to plus or minus 3 or y equal to 0. If y is equal to 0, then
X is equal to 0.
is that true? No. If y is equal to 0, what happens?
Oh, I'm sorry.
There's
This
something
the
a bit,
third equation, right? I'm
there's
sorry.
something a bit strange over here, right? So right. So if okay, right. So okay, exactly. So you see, y equal to 0 is sort of ruled out. Why is y equal to 0 ruled out?
Because then x is equal to 0 and it will not lie on the ellipse.
Correct. So whichever way you want to do it, or if you want to look at the third equation first, then if y is equal to 0, then x will have to be plus or minus 3. But then the Lagrange multiplier constraint will not be satisfied. So not possible, etc. And now once I have lambda equals plus or minus 3, then you solve. So get get 4 solutions. Now the fact that you have 4 solutions, that should not be surprising. Look at the picture in the beginning. It's going to be a rotated picture as far as all those hyperbolas are concerned, the level sets. But instead of the circle, it's going to be an ellipse. And in any case, my circle is so terrible that it's closer to an ellipse. So the fact that you are going to get 4 answers is all. So etc. So do the algebra. And find extreme. Again, in this case, whatever is the maximum and minimum, it's just a matter of plugging in, right? Because this is going to be an ellipse. Find extrema. As constraint ellipse, a compact set. Just evaluating F on candidates. Is enough to candidates is enough to find extreme maximum. Okay. How about number 5? How are we on time? Okay, so we have a little bit of time. Maybe we can just set this up. So here, what is the function f? Geometrically, we should be able to visualize this. So what is the function f? Come on. So the function is going to be square root of x minus a the whole square plus y minus b whole square plus z minus c the whole square, right? Of course, we can try to maximize or minimize this, but it is easier to maximize without taking the square root. No, it's really the same. So x minus a the whole square plus y minus b the whole square plus z minus c the whole square is here without square root. And it's equivalent, right? And h is equal to x square plus y square plus z square. Constraint is this is equal to what did we have? 9, whatever, something. So shall we do this or can I leave this to you?
I'm sorry, you can leave it.
Yeah, so so complete this. The geometry, so complete this. And complete this and reconcile with and see that geometrically obvious image. Okay. All right, good. So now exciting. So let's define the tangent space. So definition. Tangent space to a hypersurface M is equal to so shall we hypersurface M is equal to F inverse of C for okay. So you know while I'm doing the verbiage, here is the thing. So M is equal to F inverse of C, where F is some function. In Rn, where F is, let us say U open Rn to R is a C1 function and C is some. In other words, this is just a level set. So here's an example. So in this case, n is equal to 2. What is the function f? F of xy is equal to
X minus y square.
right, or rather y minus x square, the way I have drawn it. And I'm taking this and m is equal to f inverse of 0. And let us say to a hypersurface of course, there are lots of tangents, right? So at a point P, so let's take a nice point here. Let's say what. So this point is 3,9. So 3,9 is in. So what do we want this tangent space to be? And the answer is, well, we know what it should be. It should be this nice line. But our definition is going to be slightly different. So definition. So I'm going to define this to be a subspace of Rn. So definition is is a subspace of Rn sorry, this is now become an interview. I do not want to define to be Tp of M, and that P I want to be. So this is very simply the kernel of the map F prime. Sorry, F prime of P. Okay, so now let's just let's just get our bearings right to see that this is not an unreasonable definition. It is not going to correspond to that red line that we do, but it is going to correspond to something pretty close to it. So what does this mean? This simply means that all of those vectors V in R such that F prime V evaluated on V is equal to 0. But notice this is really the same thing as the following. Now this F prime of P, what kind of gadget is it? So recall, F prime of P is a linear map. From where to where? From Rn to R. Remember, F is a function from something in, from Rn, a real valued function. So right now, later on, we will generalize this to functions that take values also in multiple dimensions. But for now, we are sticking to the case of a real value function. So F prime of P is a linear map from, from Rn to R. So I'm simply saying, take the kernel of this map. All right. Okay, so let's in the example. In the example here, so what is the map? So here, what is F prime of P? What map is that? So it's going to correspond exactly to your visual intuition up to a shift. But we should understand, abstract language is useful in extending our ideas, but then it should not become a burden. So what is the meaning? What does it mean to calculate F prime at any point? Remember, F prime is a linear map. A linear map in this case from R2 to R. But a linear map is given by a matrix. Once I choose a basis. With respect to the standard basis, what are the matrix entries of the derivative as a linear map?
Minus 2a and b, if we
Right.
consider.
I mean, in other words, it is just the partial derivatives, right? Matrix of partial derivatives. So what are the partial derivatives over here? I simply calculate the partial with respect to x, so that is minus 2x, and y, but evaluated at 3, 9. In other words, this is, what is the map? Oh, sorry, what did I have? God, today is really my mistake, I mean, well, I make mistakes all the time, but today it's worse than usual. The second entry should be
1.
1, exactly. So, in other words, this is just the matrix minus 6, 1. Now, if you think of this as a map, what is the kernel of this map? Sorry, so I mismanaged over here. I really should have done this example later. So in our example, prime of P is from R2 to R. That has matrix minus 6, 1. So if I take the point U, V, sorry, let's write it as a vector. It's a linear map U, V. Where does it go?
minus 6u plus 1.
Yeah, and in fact, at the risk of hopefully not confusing you, let me call this also x comma y. Then what is this? It goes to minus 6x plus y. And therefore, the kernel of f prime of p is the set of all x comma y such that y equals 6x. In other words, I did not get the red line, but I got this line. And the reason for this is absolutely clear, because when I take the kernel of a map between vector spaces, the answer to that is going to be a subspace of the original space. Of course, it will pass through the origin, right? So this is called the algebraic tangent space, to distinguish it from what we regard as geometrically as the top tangent space. So we can say to our visual, to our not visual, is equal to Tp of m plus. Okay, so is that clear? I hope that. So what do I do? This point, which is the origin, is over here, right? So I shouldn't have used it for that. This origin, I simply add the point P as a vector to everything on that red line, and it will simply shift. Okay. Now, a little bit of sort of thing to keep in mind is that if I give you this red line, and if I simply erase the curve, everything that associated with it, and if I say that, oh, this is the tangent space to something, will you be able to tell me what point it corresponds to the point of tangency?
No, sir.
Just that shifted line itself will not tell you. So if you really want to think of this, red thing as a tangent space, then what you should keep in mind is not just this set of vectors, right? So I will just say, but also keep track of the, but also keep memory of the point, not just that as a set. All right. So this is the definition of the tangent space. All right. So okay, we are well out of time. Just tell me one more thing, and then we will stop. So you should really get used to this notion of tangent space. But we can now think of this slightly different. So f prime of p, if I write instead the gradient of f, then what is the connection between the gradient and f prime? F prime is a row vector. Gradient is
The column vector of the
column
the
vector.
transpose. Yeah.
Right. So it's just the transpose. And now v also is going to be a vector in the original space. So evaluating a row vector on a column vector, if I change that row vector to a column vector, then what does that operation correspond to? Instead of evaluation, now it just becomes
Dot product.
dot product. And visually, visually this is very nice, right? Because what we are saying is that now tangent space, instead of this kernel of an operator, I can simply say that, well, just take the gradient as a vector and simply calculate everything that is perpendicular. So this is, so that is the definition of the tangent space. So this is called the geometric tangent space. All right, so we are on the cusp of saying something very interesting, but we are out of time. So we will stop. And in the next class, we will we will see the proof of this, but we will run into some roadblock. And in order to get rid of that roadblock, we will have to go to implicit function theorem. So that's what we will do on Wednesday. So let's stop for today.
Recording stopped.
So this is the definition. Okay, so that's where we are headed next. And we should be able to, I think, finish this by the end of this month. Or maybe just in one more class. All right, so let's stop for today, unless there are any questions or comments. Yeah, so one more thing, which is that, so you're going to get the homework very shortly, and you will have, we will have, I think, 3 more homeworks. For each one, I will give you a week. But we would also, every homework should also be followed by a quiz. And now I do not want to take out class time. Because for both quizzes, there were some complaints that the time is not enough. I'm happy to give more time, as much time as needed, but then we need to find time outside class. So that may mean that some evening or something like that, whatever is a suitable time for your class, you should sort of discuss and tell me. So I'll ask you in the next class.
Sir?
Yeah.
So how many classes do we have in May?
So we will have classes till the end of whatever is the official period of classes. We will have all of those classes. Then then there is 1 week. Okay. So what is the final official date? Let's see. In May, I think officially the last class is on the 6th. Is that right?
Don't know, sir. I'll have to check.
Yeah, I think it is 6th. Because the following week was supposed to be the finals week. But you're not going to have finals during that week. I would like to hold classes during that week, but as I said, whatever is beyond the official portion, none of that will be in the exam. So we can have problem solving sessions in class, or we can discuss other stuff. So during 9th to 13th, I would like to meet. We will have classes, but it's up to you whether you want to. I think that we should have absolutely no problem finishing everything that is, that is our main brief by the 6th.
Okay, sir. Yeah.
And we will have classes 9th, 11th, and 13th. Your exams are going to start on the 18th, right? So 16th, we will certainly not have a class. Your exam is on the 22nd, and so chances are that I will be at CMI for the entire day before that. That is the 21st. So if you want to meet me or ask questions or discuss, I will be available for that entire day. I mean, I'm available even beforehand on the phone, but on that day I will be there physically in CMI. This is the 21st of May. By the way, but we, one second. Okay, so, all right. No, I just sort of realized that I miscalculated the time that is left. So we'll have to rethink a little bit. But anyway, I'll get back to you in terms of timeline for whatever is left. So, okay, anything else? Very well. So let's stop for today and we'll meet on Wednesday.
Thank you, sir.
Thank you, sir.